Okay, so group theory. So let me just go over the last couple of slides here. Groups have been defined through their axioms. Okay, so and then we derived everything else from those axioms. Okay, so we ideal. That's what makes group theory, deriving things from a explicitly set up set of axioms. But then there's you don't want to really. I don't want to do it in this class that much. So we did do a bit of that. So we have derived. What did we derive directly from? For example, the cancellation law, like you see over here on the left. Okay, so it is derived directly from the axioms and nothing else. So it doesn't matter what that group is. The axiom always holds. Okay, so and then you can derive the whole theory about a lot of different things, non-specific to any particular group, but it applies to every group that we can think of. So that's one example, and then out of many, you'll have to take the course in modern algebra to see more. And then we did some examples of where we really go to the bottom of ultimately of algebra, what algebra is, and that is the good example was the groups of integers modulo n. Okay, so that's the example that we have pursued, which is simple enough and hard enough at the same time, so that it gives all the idea of how algebra works out exactly the same way, except in a setting that is entirely different from what we used to. Okay, so this is the group. Okay, so we defined. I want to make that point again of how we define the algebra of operations, how we define operations, what it means for two elements of this group to be added together. And the answer is not really this. I mean, it is ultimately this is the definition of addition in Zn, but also remember this is what we did another way, and it is ultimately every element of the group is in a Coulom's class, and therefore it is a subset then of all the integers. And then how do we add two sets of integers? We just do it by one by one. Okay, everyone from here, everyone from there, pick together, add them together, put them on another list. Keep adding them together, creates a big list. Okay, and that new set is the product. And turns out, because of the way things are set in this group, it turns out that formula on the right, in the purple, is actually what works out. So, okay, all right. So subgroups. Now that's what really the structure where the modern algebra is about. It is structures of groups, and just as an example to see what it means, it is a subgroup. So groups that have that to begin with are subsets of our group. Every group is a set, right? It is a pair of set and operation. So suppose you take this subset of that set with the same operation. Okay, so you're not trying to do anything else. Take the same set, take a subset, and carry out the same operation on it. Okay, so the easiest example, of course, is the real numbers and integers. Okay, so integers are a subset of reals, operation is exactly the same. Okay, so it is more interesting with these groups, this a band. And this is so the list of groups starts with the group 0, okay, and one element, and then we discovered more elements by simply examining the addition table, the one on the left, okay, and then we the next one on the right is the picture that gives us the addition table of the 0 group, right? So this one is the 0 group. Right here, we just extract this little table from it, and then we try to find bigger one, and turns out that if you just enlarge it too slightly, it's not going to work out. It's not working out because 1 plus 1 is 2, and we are outside. Unlike the group, remember the group. Why a table like that forms a group? Because there are no other elements So if you have elements from 0 to 3 in the rows in the upper top row in the column on the left, then whatever operations you carry out will produce once again elements of that group from numbers from 0 to 3. Okay, so that's why it works out. The rest of the axioms the axioms may have to be verified, right? But at least the operations would not take you away from your group. Okay. So by the way, taking operations takes away you from your group. Well, think about, for example, when it does happen. Think about division. You start with integers and you try to divide. You divide 1 by 3 and suddenly it's not an integer anymore. So it is typical, actually, so many operations. If you start with positive numbers, you subtract, you have negative numbers. It's all once again out. You're doing real numbers. How about you take a square root? And you have might not have it might be a complex number. Okay, so it is typical, so we have to verify that. Operation is very simple. It's addition, but still, well, not addition, just any addition, but the way we have defined it right there. So that's the alternative way of writing the same thing as that I just showed you. Right, this one. This is still our addition of numbers between 0 and 3. That's how they added together. Turns out the axioms are satisfied. Okay. So we have a subgroup. Then the blue group on the right doesn't work out because, well, 1 plus 1 is 2. And we are out, and then we try to enlarge it to 0 and 2. Once again, it's not working out because 3 is there. And finally, we were able to, that's at the very end, we were able to find one, and it is if we choose 0 and 2. Then 2 plus 2 is 0 in the group of Z4. Okay, which means that it is as we, the way we describe it, it is, so G is closed under this operation. Okay, closed. So naturally, the group itself, Z4, is closed under its operation. But then that, as you can see, doesn't always work out if we pick a random subset. And then we extracted whatever we marked on the left, created a new group, and that becomes addition table with the same addition of this smaller set, and it is closed. And since all the axioms are satisfied for the bigger group, then they will be satisfied for the smaller group. Well, but by that I meant commutativity and associativity. But there are other groups and other axioms to worry about. What are the other two axioms? Associativity, commutativity. What are the other two? Zero. So we have to point out in this new group, the conjecture is this is a group. Okay, so like I said, associativity, commutativity, it is simply they are inherited from the original group. Okay, but what about 0? Well, 0 is 0. Okay, fortunately, that doesn't have to be. Well, doesn't have to be necessarily this way. So 0 is 0. Okay, but that works out. As you can see, 0 plus 2 is equal to 2. Okay, that works out. That one axiom, and the other one is the negative. Okay, so. And well, negative of 0 is 0, negative of 2 is what? What does it mean to be the negative of an element? What does that axiom actually say? It has to cancel the element itself. So, what's the formula?
X plus negative x equals 0.
Okay, so what do you have to add to 2 to get 0?
Negative 2.
Negative 2. Okay, so negative 2 is, but there is no negative 2 on the list. So So negative 2 is not negative 2. It's negative of 2. You see how we're looking at it? There are negative numbers here, so we don't have that luxury. So we have to point out on our short list only 2 elements. Which one is it? 2. It is 2. 2 plus 2 is 0. Okay, there you go. It is its own negative. Okay, because it's mod 4, that's how it works out. So incidentally, since we're talking about, maybe it makes sense to go and look at the original group of Z4 and make sure that we know the negatives. So the negative of 1 is no 3. What do you add to negative to 1 to get 0? Mod 4. The answer is 3. This still works out, and the negative of 3 is 1. Okay, so it is mod 4, so you need to add as much as what's left to get to 4, because 4 is 0. Okay. So so the 0 is here. The last step now, that's a crucial step. This one, to take that group that this here is a subgroup, but we want to go beyond that, and then we discovered that it matches in some way, whatever that means exactly, just yet it matches the behavior, the algebra of the group Z2. In what sense? It is just renaming. So all we have to do is just to rename 2 as 0. I'm sorry, 2 as 1. Okay? And the operations are the same. So instead of having 2 plus 2 is 0, we have 1 plus 1 is 0. So so it's certainly, you can say it is different. If you think of these two groups as concrete groups, then you'd say that they are different. But as an abstractions, they are not. Okay, so that's the way it is done then in modern algebra, is to say that these two groups are equivalent. In the same sense that we have been talking about, equivalence relations. So if you can match up the elements of the group as well as their addition tables, then they are equivalent because they have exactly the same algebra. Okay, so you can certainly see more and more complexity of in this you can see more complex examples of that, such as, for example, if I want to think of a match for my group Z4, the original one, so whatever adds up to 0 after, so 1 plus 1 plus 1 plus 1 is 0. That's something what I'm looking for. So some element that actually, when added to itself, gives me 0 in some sense. And the example would be, so Z4 is equivalent to, the word is isomorphic, but we're not going to use it, but just worth mentioning, to what? Here's a group, 0, 90, 180, 270. What am I talking about here? Rotations, right? These are rotations, and indeed when you rotate 360, you have 0. Okay, so the algebra works out 90 plus 90 is 180. But if you add 180 to 180, you'll get a 360, which is 0, right? Because rotation comes back straight to, so it becomes a 0 rotation. Okay, so it's the same group. So we do not distinguish between this group, well, in the abstract setting, you do not distinguish between the group Z4 on one hand and this group H of rotations. Okay, so that's because you want to have it as few as possible groups, I suppose. So you rather put them together. If they do not have any difference as far as algebra is concerned, there is no difference. So why treat them separately? And then Z4 is a good example of this, Why? Because it is the simplest. You know, if I have a group of 4 elements with this property, what is the simplest one? You just put numbers between 0 and 3, and you just carry out addition mod 4. Okay, and that you have that one. And this one is actually H is no, H is Z4. So I don't want you to think that this is the same as Z360. It's not exactly the same. Why not? Z360 will add up to 360 and become 0, right? So what's the difference between Z360 and Z4? That's right, and this one 360. So the same idea, but it's just smaller. That's all. So rotations are only taken 90 degrees at a time, and this one is 1 degree at a time. Okay. So that's what you get. The subgroups, back to subgroups, and there are more interesting groups, and they have more interesting subgroups. But first Z4. So Z4 contains Z2. Okay, so that was our conclusion. But what does it mean that it doesn't have anything else? And it does. It's just not. Well, it sort of contains another copy of Z2, and it's just harder to see. So then Z4 is made of 2 copies of Z2. Let's take an example which is more explicit in that manner, which is it allows a simple decomposition, and the group is Z6. So let's take Z6. So once again, 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. Okay. Okay, like this. Right. So this is my group, and let's investigate subgroups once again. Hold on, so 0. Okay. So as you can see, the pattern is clear. I mean, the operation is simple. So you can see how 1s, 2s, and 3s go diagonally this way and that way. It's all very predictable. Okay. So first of all, the 0 groups is there. 0 subgroup is still there. Could you please close the door? Okay, so addition group of Z6, 1 subgroup is right there, the 0 group, which is always a group. I mean, you take any group and you pick 0 as one single element, it adds to itself, so that's always a subgroup. Z2, well, let's find Z2 first. Do you see the Z2? Z2, remember what Z2 is. It is, for one, it contains 2 elements. One of them is 0, right? 3 and 0, that's right. So let me mark it. So 0 and 3, 0 and 3. And when we add 0 to 0, 0, this is 3, and we have 0, right? It works out perfectly. So it is 0, 3, 0, 3, 0, 3, 3, 0. So that's the table of Z3. So we have found Z2. We have found Z2. What about Z3? So Z3 has 3 elements. Okay? How do they operate? 1 plus 1 is 2. 2 plus 1 is 0, like that. So in other words, it makes what the similarity between all those groups is they're cyclic. In the sense, if you keep 1, 1, 1, 1, you end up backwards. How many steps? That's in Z2 it takes only 2 steps, Z3 takes 3 steps. So what is the number you add to itself 3 times so you can get back to 0? Mod 6. 2. 2 plus 2, 4. 4 plus 2 is 6, which is 0. So 0, 2, and 4, we're going to need these. Okay, let me mark these. And indeed, everything works out. We do not have any extra elements that we don't care for. Okay, so 0, so this is Z3, is 0, 2, 4, 0, 2, 4, 0, 2, 4, 2, 4, 4. Okay, 2 plus 2 is not 0. This time it is 4. But 4 plus 4 is 2, right? Mod, everything mod 6. 2, and 4 plus 4 is, hold on a second, where's my 0? That's right. 4 plus 2 is 0, and this is 2. Okay, so a very, very simple matrices, or tables rather, because they still, the order of, still continues. 0 to 4, 2, 4, 0 is there in the same order, just with a shift. Okay, every row is the same, only with a shift. And every column is the same, only with a shift. Okay, so there is also symmetry. The diagonal symmetry is also preserved. The 0 remains the same. The first row versus first column are identical again. So that's the way it goes. Okay, so we found Z2 and Z3. Do we have Z4? So we found 0, we found Z2, Z3, and what about Z4? Well, once again, it has to cycle back to itself, right? So, well, first of all, Z4 has 4 elements. Okay. Zeros, it still has to contain 0 to begin with, so 0 and 0. And now we pick one of these elements. Is it 1? So does this group contain 1? If you start adding 1 to itself, what's going to happen? 1 plus 1 plus 1 plus 1. So how many times do you have to add it to itself in order to come back to 0? 6 times. 6 times. Right, so it means it's not 1, because Z4 is supposed to contain 4 elements, so it's not definitely not 1. Okay, let me cross it out. Not 1. 2 has been taken, and 4 has been taken too. I'm sorry, not 4. The 3 has been taken. Okay, for Z. For that group, and we're left with 4 and 5, and they are also in the wait a minute, where is that? 4 is also has been listed. Oh, it has been listed in Z3. 4 has been listed in Z3. The 5 has not been listed anywhere. Why is that? Well, what is the how many times do you have to add 5 to itself in order to get 0? 6 again, right. So it is, in a way, it is the same as 1. Okay, so So what we're talking about here is the generators. So first of all, there is none. The answer is none. Okay, it's not here, and in fact, there is nothing else. There are no other groups. So there's 0, Z4, and Z2. That's it.
So we can't use numbers that are in different groups for different groups?
No, they do. Well, first we did. They both contain Z2 and Z3 both contain 0. So they do overlap. But well, we certainly you cannot include 1 and 5 because the operation is the same. The operation is the same. So which means that if it takes 6 times to add 1 to itself to get 0, it will have the same property inside of the new group. So that's why 1 and 5 cannot be in this new group. Okay. Why cannot be 2 and 3 is a little bit more subtle. Why cannot you have 2 and 3 there? It is so well you can think of it this way. If we added 2, suppose we have 2. Suppose let's include 2. So then we have 0 and 2 in this new group. Then we still need to. Well, I think we already run out of elements. I discarded. Wait a minute. Let's see. I have discarded 1 and 5. Okay. And I am left, well, it is actually plausible at this point. Let's approach it this way. So I discard 1 and 2 because they are two, they take 6 times to add together to get 0. It's called the degree. Okay, but we are left with 2, 3, and 4. Okay, so which together with 0 might form Z4, hypothetically. So 0, 2, 3, and 4. That's the only 4 elements that we have left, and coincidentally we have the group with 4 elements. We just look at this, what's left, and see if this does form a group. So, well, let me do it. So suppose these are the only ones that are left. Okay, so this is 0. This is part of my group 2, or part of my table, and this. Okay, so you can see that it doesn't work out, because adding 3 to 2 gives me 5. Okay, which is not on the list. Okay, so there are theorems for shortcuts finding subgroups certainly, but for this time you appreciate them when you do it a little bit trial and error like we did here, and so to demonstrate that there are indeed no groups of any other no any other groups, Z2 and Z not, Z2 and Z4. So in fact this is how it is written. Z4, which way do we go? Let's go up. 0 is a subgroup of Z2, is a subgroup of Z3, and both of these are subgroups of Z4. Okay, so this is a hierarchical structure of subgroups of this group. The bigger the group, the more of the more structure you have like this. Okay, so they're more like a so it could be a very large diagram like this. What is so special? I'm sorry, I was talking about Z6, not Z4 over here.
Real quick, you said we can't use 3 because 3 plus 2 is 5.
Yeah.
But why is that outside of Z4?
Right, and 5 is not on the list. So we pick the list 0, 2, 3, 4. And it is not a subgroup because 2 plus 3 is 5. Okay, so so to demonstrate that there are no other subgroups is a challenge. So for example, we found Z2, maybe there are other Z2s hidden there. We found a copy of Z3, maybe there are more copies of Z3 hidden somewhere. And then we more or less made, I think, pretty good argument why there is no Z4, and you can also have to make an argument why not there is no Z5 there. So it's all possibilities to work out why the diagram is as simple as this and there is nothing else. It takes some build-up. We'll just look at the trial and error. Trial and error it is sufficient for as long as they're small. Okay, so well, this is once again how you proceed into discovering discovering patterns, and the pattern is, you can see if you look at that, we have Z6 and we have Z2, Z3. What is the pattern? What is the relation between 2 and 3 and 6?
2 and 3 are factors of 6.
Yeah, the only factors. So they divide, both of them divide 6. And in fact, so 6 is equal to 2 times 3, which means that turns out that every element on the list is there. And that is the pattern, that is a theorem that needs to be proven. So if you have a group of say, well, if you can try to guess a group of order 12, then Z12. Okay, so 12 is equal to 2 times 4 or 3. Okay, then there will be Z2 and Z3. It is trickier when we talk about when there are multiple factors. Then subgroups might not be recognizable. Once again, if we go to the previous example of Z4, 4 is 2 by 2, 2 times 2, and however we only found one subgroup of order 2. So even though there are two, the factor 2 is repeated, but it's not the same. Okay, so it is. So what is the difference is then between Z4 and Z6 we just considered is that whether there is a repeated or there is no repeated factor. Okay, in the prime decomposition. So that's what the class started with. Remember decompositions of prime decompositions of numbers, and so that matters when you try to find the structure of the group. Then the prime decomposition of its order Z sub something n will depend on the decomposition. And the multiple roots, multiple factors rather, are they kind of complicate things. So you can convince yourself if you try to, once again, is there another copy of Z2? So once again, look at Z4. We found one copy of Z2, which is here, right? Right here we found the Z2. Is there another one? So if instead of 2, then if you pick anything else, you try pick 1. No, it will give you the whole group 1 plus 1 plus 1. You're not going to get to 0 until you do it 4 times. Same with 3. You have to add it 4 times in order to end up with the 0 mod 4. Okay, so there is no other copy of Z2 here. Okay, so so where is it? And I wonder if I can demonstrate that there is another copy of Z2 hidden here. Okay, let me try. Okay. Okay, so what I'm going to do, so this is Z4. How about, the order really doesn't matter, so how about I rearrange the terms? How about I go 0, 2, 1, 3. 0, 2, 1, 3. So it doesn't matter, right? It's the same algebra, so it will be 0, 2, 1, 3, 2, 1, 3, 2 plus 2 is 0, 1, 2, wait a minute, not right. 2 plus 1 is 3, and 2 plus 3 is 1. Okay. 1 plus 2 is 3, 1 plus 1 is 2, 0. 3 plus 2 is 1, 0, and 2. Okay? So, once again, every number appears once in every row and once in every column. Okay, so now this is the trick of how we can see another copy of Z2 here. Here it is. Well, like this. Well, first of all, you can see I put the boxes on the number, combine 0 and 2 together and combine 1 and 3 together. Okay? And then, so, do you see what I'm talking about here? What?
You have 0 and 2 as one part of Z2, and then 1 and 3 is a different.
That's right. So this will be 0 of my Z2. I'm looking for another copy of Z2. Okay? In addition to what we already had. And then I created, by means of combining elements of my group Z4 together, 0 with 2, 1 with 3, and I named these as 0 and 1, which will make it into Z2. So the only thing remains to confirm that indeed it is gonna, the operation works out the way we want. That table that I have created, it's not only the list of the group at the top, but also there's multiplication. So I have to verify that when I multiply 0 by 0, this new 0, I will get 0. Look at it. Can you justify it? 0 times 0 is equal to 0. Can you justify this based on the table?
Yes.
Yeah.
How?
Because,
Because the only spot where 0 and 0 cross is 0.
No, I would do what we just did. Remember at the beginning, if you multiply, or adding two sets, you do it pairwise, all possible pairs. So I have 0 and 2. I add them together with all possible possibilities. So 0 plus 0, 0 plus 2, 2 plus 0, 2 plus 2. What do I get as a result? I get only two numbers. This is 0 and 2, right? So 0 and 2, and that, what is it? It is 0. It is 0 in my new group. On the other hand, if I move to the next one, I'm multiplying 0, 2 and 1, 3. Okay, so I'm here. 0, 2 and 1, 3. I'm multiplying them pairwise. What do I get? According to my table, I get 1 and 3, which is the same as our 1. Okay, similarly, it's here in this one, 2, 0, 0, 2, this is 2. So that way I do get this table, which is exactly as planned, right? That's what we get. So we extract from our table of Z4, we extract in a very different manner, we extract a group of C2, which turns out to be there, but I want you to connect this idea to something that we have been talking about for a while, operation on sets. So I'm talking about what? I'm talking about the Cohen's relations again. So I do not just extract a subgroup from Z4 as we did on the previous occasion. 0 and 2, that's it. It is a subgroup. This isn't a subgroup technically, because it is a group of equivalence classes. Of equivalence classes in this subgroup, it just happens to be Z2 by equivalence, but other than that, it is you cannot really see it in the table on the left. You cannot say, well, it is a subgroup, because this Z2 is not a subset of our group, but rather it is a subset of what? Of the set of subsets, I guess would be a fair way to put it. So they put it, so this is once again is the quotient, the quotient construction or equivalence. So these are equivalence classes. So, and that's how you use Z2. That's how you find Z2, another copy of Z2 in Z4, and that is inevitably the case when you deal with repeated or multiple factors in the prime decomposition of your group, of the order of your group. Okay, Z6 we just worked out because there is no repetition. Then both of the subgroups, Z2 and Z3, we were able to find explicitly without going into this complex construction. Okay, so these are one's equivalence classes. And you can certainly tell what those equivalence classes are. I combine 0 with 2 and 1 with 3. What is this? What are they? What are these two classes? Well, either it is or is not divisible by 2, right? So they're still what are they? They are mod 2 equivalence classes, or congruence classes. 0 is congruent to 2, and 1 is congruent to 3 mod 2. So that's how we combine them.
And this right table where you have boxes and whatnot, you with the 0, 1 on the tops.
Yeah.
When you did the pairwise adding those sets. And whatnot,
Yeah.
Can you run through that again?
Okay, so let me write it out. So what I'm talking about here is 0 is 0, 2. 1 is 1, 3. Well, yeah, let's do 1, 3. Okay. So these are the two classes. Now I carry out addition. 0 plus 1 is 0, 2 plus 1, 3. Pairwise, I will have 0 plus 1, 2 plus 1, 2 plus 1, 2 plus 3. Okay, what are these? According to our, all of this is addition mod 4, right? Because everything is happening in Z4, so whatever we're dealing with is mod 4, so it will be 1, 3, 3, and 1. Or in other words, since it is a set, we are not allowed any repetition, so it's 1, 3, which is 1. Okay? So you can carry out with that with the rest of them. Okay, so so as an exercise, so try the same for say well, start with Z5, and then what is in the order that we have skipped: Z7, Z8, Z9. Oh, these are still weird numbers, and Z10. So any predictions about Z5? Say. What are the factors of 5?
1 and 5.
What?
1 and 5.
1 and 5. So what does it tell you about the structure of this group in terms of subgroups?
It's only subgroup is 0.
There is only subgroup. So you can say that the group itself is also a subgroup. So there are two trivial subgroups, the 0 and the group itself. So nothing non-trivial then. Z7, same story. Right? Z8, however, is complicated because not only you have a repeated factor, it's actually cubic. Right? You can probably guess, so that would be somewhat of a challenge, but you can guess what Z9 behaves like in analogy with Z4. Right? So this is the biggest challenge. This one is familiar. Z10, what are the subgroups? Z2 and Z5, nothing else. So these are two factors. There are no repetitions, so we don't have to worry about. Okay.
So if there's repetition, you have to demonstrate that, like state Z8, for example, it's 2, 2, 2, 2, 2. Well, we have to find 4, or demonstrate that you can get.
Well, right now we don't have any other tools, so this is pretty much it.
Okay.
To demonstrate that.
So we just have to demonstrate that works.
Right. Don't try to, when the group is too large, trying to prove that there are no other groups, it might be too much work. But at least finding all the subgroups that are supposed to be there, and that would be good. That would take care of it. Okay. So these are the groups, subgroups. And then there are functions between them, so that's what that match is that I pointed out. And you can't really study algebra between the operations between them. You probably noticed that in calculus, after all, you don't study real numbers, are you? You're studying functions between real numbers, that even calculus 1. So similarly, you don't study groups without studying operations between them, or not operations, functions between them. Okay, so except unlike the set theory functions that we saw, there would have to be, there's an extra structure. So this is not set theory anymore. We have algebraic structure on our sets, which means that the functions that we are looking at should not be also just any function. They should preserve operations. Okay? where else do you see it? Operations, you usually you don't. But this is the what you expect to have is like this: f of x plus y is equal to f of x plus f of y. So that's what preservation operation means. But let's just leave it alone because it just would take too much time to get into it. I think we got an idea of what groups are, and there's some interesting exercises are just could be done with trial and error. And every time you do something, try to see a pattern if there is the pattern for you to discover. So we discovered. I didn't even put it in writing, but you can guess that for each. Well, I guess let me state it. A Zn has a subgroup for each what I meant subgroup Zm, say Zm for each m divisor of n. Okay, so that's what we try to illustrate. What do you? I wonder if you want to add anything to this theorem.
Unique divisor?
You mean a unique subgroup? That would be an interesting question indeed, and it is true, but in a sense, it just what unique subgroup means is not exactly. No, it is more or less clear. What it is true when the divisor is unique, then the subgroup is unique too. So when there is no repetition. Okay, so but when it is not, when there is factor is multiple or divisor is multiple, then we cannot say that anymore. Okay, so that's good. Anything else? Well, let me put it this way, if I can restate it. If M is a divisor of n, then there is a subgroup Zm in Zn. Okay? What else? How would you proceed from that point on? If we take this as for granted, what else do we want to explore? The opposite direction? What am I talking about? There's a word for it. No, close, but not inverse, but converse. The converse, right? So every theorem is if-then, and there is always an issue of converse, and that is relevant. We did come up just because there is a subgroup for each m. Does it mean that? What about? Is there other groups? And the answer is no. So conversely, so there is, or there is nothing else. Conversely, if G is a subgroup of Zn, then its order, then G is M, where M is a divisor of N. I don't want to say that it is necessarily a group of Zm, so let me maybe simple G. Okay, so just the size of the group is M. I guess this would be in order, an example of a group that is, say, have n elements, but not, well, I'm out of time, I'm sorry. Okay, so we'll just finish next time, sorry about that.